We now take up the second derivative test. Before this, when I talked about the first derivative test, so we had an interior point in the domain of a differentiable function, and it was a stationary point. We took the first derivative test to check whether it was a local maximum, a local minimum, or neither. And in that case, we just checked the sign of the first derivative to the right and to the left of the stationary point. So that was the first derivative test, and now we take up the second derivative test. If I talk about the second derivative test, for that we suppose that we have a twice differentiable function. So let's say we have f is a twice differentiable function in an interval I. And when I say it's a twice differentiable function in an interval I, that means it is differentiable in this interval and it is differentiable again, as in it is differentiable 2 times. So we can find the first derivative in that interval. We can also find the second derivative in that interval. That means f is a twice differentiable function in that interval I. Suppose C is an interior point of I. So again we get to the interior point of the domain of a differentiable function, but in fact here we say that we have an interior point of the domain of a twice differentiable function. So if this is the case, these 2 points to be noted, then number 1, f prime c is equal to 0 and f double prime c is less than 0. So C is an interior point and let's say C is a stationary point. Now let's take up the second derivative test to check whether the stationary point is a local maximum, whether it is a local minimum, or it is neither. So f prime c is equal to 0 and f double prime c less than 0. This implies C is a strict local maximum point. Then let's say f prime c is equal to 0 and f double prime c is greater than 0. Then C is a strict local minimum point. And the third point to note is that f prime c is equal to 0 and f double prime c is equal to 0. Then what happens? Then in fact I can write anything can happen. That's very important. I'll explain after that how this is the case. That when I say what do I mean when I say anything can happen? Now what we now do is we prove the first point, and if I prove the first point, I can easily get to proving the second point. So just to understand this, we prove the first point here. And when we do that, first obviously we have to start with f prime c equal to 0, f double prime c less than 0, and then we have to get to C being a strict local maximum point. For that, what we do is, so let's say f prime c is equal to 0 and also I have f double prime c less than 0. f double prime c is nothing but the derivative of f prime x at c. So this is nothing but the derivative when we differentiate f prime x and we evaluate that derivative at c, that gives us f double prime c. So it is the derivative of f prime x at c. Now that means I can write f double prime c is equal to limit h tending to 0 f prime c plus h minus f prime c divided by h. That's just what I have used. Here I have used the definition of the derivative, and I know that f prime c is equal to 0, so this is nothing but limit h tending to 0 f prime c plus h by h. I know that f double prime c is less than 0. This is less than 0. And what is this? It is the limit of this expression as h tends to 0. That just means that f prime c plus h by h, this is less than 0. If f double prime c is less than 0, that means this is less than 0. Keep this in mind that h tends to 0. Now h may be very close to 0 from the left or from the right. So h may be 0.00001, h may be minus 0.00001. So the point to note is that this is sufficiently small. H tends to 0, either it is tending to 0 from below or from above. But either way, mod h or the absolute value of h is sufficiently small. Now let us suppose that h is positive. H is tending to 0, h tends to 0, but h is positive. So it's a very, very small positive number. Then in that case, f prime, I know f prime c plus h by h is less than 0. H is positive. That just means f prime c plus h is negative. So that means, hence, f prime c plus h, this is less than 0. And what does that mean? And h is positive. That means in an interval to the right of c, f prime is negative. In an interval to the right of c, because c plus h and h is positive. In an interval to the right of c, f prime is negative. In an interval to the right of c, f prime is negative, h is positive. So it's c plus h. That means in an interval to the right of c, f prime is less than 0. And that just means if f prime is less than 0, it is negative in an interval to the right of c. That means the function is strictly decreasing to the right of c. So here I say f is strictly decreasing to the right of c. And this is when h is positive and h is tending towards 0. Now let's say h is negative. And h is tending towards 0. So it's minus 0.000001. H is negative, h tends to 0. So h is tending to 0 from below. And h is negative. That just means if I take a look at this, f prime c plus h by h is negative. What does that mean? If h is negative, in that case, f prime c plus h has to be positive. So f prime c plus h has to be positive. H is negative, it is C plus H. That means we are thinking of an interval to the left of C. And what we see here is that in an interval to the left of C, f prime is positive. So that means I can say f prime is positive in an interval to the left of C. Why do I say left of C? Because it is f prime C plus H, but H is negative. So it is positive in an interval to the left of C. That means the function is f is strictly increasing in an interval to the left of C. So the function is strictly increasing to the left of C, it is strictly decreasing to the right of C, and that just means this implies C is a strict local maximum. It's a strict local maximum point for f. And that's exactly what we had to prove. That if we have f prime C equal to 0 and f double prime C less than 0, then C is a strict local maximum point. Similarly, I can prove that if f prime C is equal to 0 and f double prime C is greater than 0, C is a strict local minimum point. This is also something that can be proved easily in exactly similar manner. Now let's get to the third point, wherein we have f prime C equal to 0 and f double prime C equal to 0. As I said, anything can happen. For that, I take up three functions. And why do I say anything can happen? That means I can, in this case, if this is the case, if we have f prime C equal to 0, f double prime C equal to 0, and I say anything can happen, that means we can have a local maximum, we can have a local minimum, and we can have neither. So in this case, let me just take up three functions. First, f of x is equal to x raised to the power 4. Second, I have f of x is equal to minus x raised to the power 4. Then I have f of x equal to x cubed. If we observe, we see that at 0, so in each of these functions, we have f prime 0. Okay, for this f prime 0 would be f prime x here is 4x cubed. Okay, so f prime 0 is 0. In this case, it is minus 4x cubed. Again, 0 at 0, it is 3x squared, so that's 0. Also, if you take up f double prime x, in this case it is, so that is first it's 4x cubed, that means now it's 12x squared. Again, this is 0. Here also we see that it is 0, f double prime 0, here also it is 0. So it is 0 in each of these cases. But at x is equal to 0, this is going to have a local maximum point. I mean, x is equal to 0 is a local maximum point. In fact, we are going to see that it's a global maximum point also. Sorry, not this. At x is equal to 0, it's a local minimum point. At x is equal to 0, it's also a global minimum point. Here, if you take up this case, it is a local maximum point or a global maximum point also. And here, x is equal to 0 is neither a local maximum nor a local minimum. So we can say x is equal to 0 is an inflection point. Here we see x is equal to 0. It's local minimum point, here x is equal to 0, it's a local maximum point. Here x is equal to 0 is an inflection point. Now let's take up the diagrams. These are the ones. This is y is equal to x raised to the power 4. This is y is equal to x minus x raised to the power 4. And this is y is equal to x cubed. So here we see 0. It's a minimum point. And it's a maximum point here. In fact, it's a local and global maximum, local and global minimum here. And here 0 is neither a local maximum nor a local minimum. So 0 is an inflection point here. So that is why I say that if you have f prime x equal to 0 and f double prime x, if you have c as an interior point in that interval I, f prime c is equal to 0, f double prime c is also 0, then anything can happen. Then you can have a maximum, you can have a minimum, and you can have neither. Now let's suppose we have a function f which is differentiable in the interval I. F is differentiable in an interval I. F is differentiable in an interval I. And here we suppose that C is an interior point of I, and we know that it is a local maximum point. We already know that it is a local maximum point. Obviously it's a stationary point, but we also know that it is a local maximum point. So C is a local maximum point. Then obviously if it's a local maximum point, obviously that means it's a stationary point, it's an interior point of I, and the function is differentiable in that interval. So obviously f prime c is equal to 0. Also we know that I just cannot have f double prime c greater than 0. That is, this is impossible, because of the fact that if I know that f prime c is definitely equal to 0, and I just cannot have f double prime c greater than 0, because if that is the case, that would mean that c is a strict local minimum. From what we have just studied, that would mean that c is a strict local minimum, and that's not what the case is. I'm given in the first place that c is a local maximum point. What does that mean? What is it that we are left with? That means f double prime c has to be less than or equal to 0. So this has to be the case. What does that mean? That means this is the fact that f double prime c is less than or equal to 0. It's a necessary condition for c to be a local maximum point. We know that we have a function f which is differentiable in an interval I. C is an interior point of I, and we know that obviously if c is an interior point of I and f is differentiable in that interval I, but I also know that c is a local maximum point. What does that mean? That means c is definitely a stationary point. So f prime c is equal to 0. Also, I know that f double prime c greater than 0 is just not possible, because if that is the case, c would have been a strict local minimum point, and that's surely not the case, because we are given in the beginning that c is a local maximum point. Then what are we left with? we are left with f double prime c less than equal to 0. So f double prime c less than equal to 0 is a necessary condition for c to be a local maximum point for f. Obviously, yes, I know that f prime c is equal to 0, that's also the case, but here we see that this is also the case. So f double prime c less than equal to 0, it is a necessary condition for c to be a local maximum point. And similarly, we can establish that f double prime c greater than equal to 0, this is a necessary condition for c to be a local minimum point. And that means I can say that this is necessary for c to be a local maximum point. So I can then write this case. If f prime, not that, if c is a local maximum point for f, this implies f prime c less than equal to 0. C is a local minimum point for f, implies f prime c, not that, f double prime c it is. F double prime c, and here I should write f double prime c greater than equal to 0. Now we can take up some questions, and let's take up two very important questions. The first question is that let's say you have a firm and the firm is producing some commodity. So firm has a revenue function, this is the revenue function. The firm also has a cost function, and there is a tax also. So there is a tax being imposed on the production. Let's say it's a sales tax, think of it that way. Let's say there is a sales tax of $T per unit. So you also have a sales tax. I mean, instead of saying that the tax is on production, I'm just saying that it's a sales tax of $T per unit. Now, if this is the case, and let's say I know that there is this maximum quantity that the firm can produce, which is, and the firm just cannot go above that, so that is Q bar. But again, let's suppose that the quantity at which the profit, and R and C are differentiable functions of Q, that means the profit function, the profit is also, that pi is also a differentiable function of Q. Also, I know that there are some technical limitations, so the firm just cannot go beyond the quantity Q bar. And if the firm cannot go beyond the quantity Q bar, that just means, so that's the maximum. So the firm R and C are differentiable in 0 to Q bar, and obviously that means pi is also differentiable in 0 to Q bar. Now let's suppose that the quantity at which our profit is maximum is neither equal to 0 nor equal to Q bar, it's somewhere in between. That means, and that, let's say that quantity is Q star, and we know that that quantity is going to satisfy this case, that R prime Q star should be equal to C prime Q star plus T, because that's the in this case the first derivative of the profit function is going to be set equal to 0. Now here let's suppose that r double prime q star is less than 0. It is given to us, and it is given to us at that c double prime q star is greater than 0. Now we know that in here, if we take up this equation, q is defined, in fact I should say q star is defined in this case implicitly as a differentiable function of t. Differentiable function of t. And the question is that we would like to know dq star by dt. We would like to know what this is. We would like to actually explore its sign. Also, what we have to do is we have to compute d pi q star by dt, and we have to compute this, and in fact we have to show that, so basically we have to find out the derivative with respect to t of the optimal value of the profit function. Pi q star is the optimal value of the profit function. We have to differentiate that with respect to t and see what we get. And in fact we have to show that d pi q star by dt is equal to minus q star. So that's the question we have. First we have to compute dq star by dt. For that we take up this expression r prime q star is equal to c prime q star plus t, because here I know that q star is defined implicitly as a differentiable function of t. So from this expression I'll just write this expression again here, which is r prime q star is equal to c prime q star plus t, and I differentiate with respect to t on both sides, keeping in mind the fact that q star is defined implicitly as a differentiable function of t. So I get this dq star by dt is equal to c double prime q star into dq star by dt plus 1. Now what I can do is I can just solve for dq star by dt, and when I do that I get so here I can write this minus this dq star by dt equal to 1. So dq star by dt will be equal to 1 divided by r double prime q star minus c double prime q star. Now we know that this expression is greater than 0, and we know that this expression is less than 0, and this expression is greater than 0. That means this whole expression is less than 0. And what does that mean? That means dq star by dt is less than 0, because we have a positive numerator and a negative denominator. So, and if we have to kind of explore its sign, that just means that if what is Q star? Q star is the optimal number of units produced. The point to note here is that if our tax rate increases, our tax rate T increases, that leads to a decline in the optimal number of units produced. So as the tax rate T increases, Q star falls. That's what I mean by this dq star by dt being negative. Next, we have to compute the derivative with respect to t of the optimal value of the profit function, which is pi q star. So let me write pi q star first. Pi q star is nothing but r q star minus c q star minus dq star, and I have to differentiate this with respect to t, keeping in mind the fact that q star is also defined implicitly as a differentiable function of t. So I write d pi q star by dt, that is equal to r prime q star dq star by dt minus c prime q star into dq star by dt minus, now we have this. What we do is we apply the product rule. So first function, derivative of the second. So what I do is I just write minus first function into derivative of the second. So it's dq star by dt plus second function into derivative of the first. So it's just q star. And that gives me r prime q star. So what I do here is that I can calculate r prime q star minus c prime q star. I can just write this, r prime q star minus c prime q star dq star by dt minus q star. In fact, now I should now I can also write it this way, and minus t dq star by dt minus q star. And now I can take help from this expression that we have this. And if this is the case, that means this expression is 0 and we are just left with minus q star. And this is exactly what we had to prove. Also, what it means is that if we increase the tax rate, so we can say that, if we increase tax rate by 1 unit, the optimal profit, that's going to decline by minus, not by minus, it is going to decline by q star units. So so here what we have is this d pi q star by dt, that is equal to minus q star. This is what we have proved. What it means is that if you increase the tax rate by 1 unit, if it is negative, that just means if you increase the tax rate, the optimal profit is going to decline. And what we see here is that as the tax rate increases by, let's say, 1 unit, the optimal profit is going to decline by q star units. Let's take up another question. Let's consider a tree that is planted at time t is equal to 0. Now let us say P of t is the current market value at time t. This I know is differentiable. The question is, when should this tree be cut down? In order to maximize the present discounted value. In order to maximize its present discounted value. And here we assume interest rate is P% and R is P by 100. So let's say interest rate is 100 R% per year, and there is continuous compounding, compounded continuously. So in this case, what we see is that obviously here I know that the current market value is P of t. If interest is compounded continuously, then obviously from what we have studied in chapter 8, we know that the present discounted value or the present value is going to be P of t multiplied by e raised to the power minus rt. That's going to be the present value. So obviously it's a function of t. So let's say this is the present value. Let me write it this way. Present value is this. If I want its derivative, because if you get the question correctly, here it is written, when should the tree be cut down in order to maximize the present discounted value. So we need to maximize this present discounted value. First we take up its derivative, as in the first derivative, f prime t, that is going to be equal to, again use the product rule, the first function into derivative of the second, which is this, plus second function into derivative of the first. So for that we write this. And for this I can just write e raised to the power minus rt, and then I can just go for p prime t minus r p of t. And we want to know the time when this tree should be cut down in order to maximize the present discounted value. So a necessary condition to maximize f of t is that f prime t star should be equal to 0, because that's for that t star corresponding to which we have maximum present discounted value. So please keep this in mind, that t star, which is that time when the present discounted value is maximum, obviously it's going to be greater than 0. It is time after all. It just can't be negative. So necessary condition here is this. That f prime t star should be equal to 0. And so what that means is that I have to go for e raised to the power minus rt. I know that f prime t is equal to e raised to the power minus rt p prime t minus r p of t. I know that this expression, just take a look at this expression. This just cannot be 0. Okay? It just cannot be 0. It is not equal to 0. What does that mean? If I have to equate this first derivative to 0, that just means I will have so I can then write the necessary condition. P prime T star is equal to R P of T star. That's the necessary condition. That means the tree has to be cut down at time T star, and at time T star, and T star is characterized by the fact that P prime T star is exactly equal to R P of T star. So P prime T star would be, we can say that increase in P prime T star is nothing but the increase in the value of the tree over that time interval. So P prime T star, we can say this is approximately equal to P of T star plus 1 minus P of T star. Think of it that way. So what is this? This is the increase in the value of the tree over the time interval T star to T star plus 1. And this is the increase in the value of the tree. That should be equal to R multiplied by P of T star. And what is this? This is when you invest the amount P of T star and you get the interest, and obviously you are investing this amount P of T star at interest rate R. So this is the interest that you would obtain over this time interval. Think of it that way, that for one time interval, for one period of time or one interval of time, this R is what you get. So that means we can say that what is this? This is the interest you would obtain over this time interval, which we have considered to be really, really small, when you invest amount P of T star at interest rate R. So that is R multiplied by P of T star. So necessary condition here, I can write it this way, that the tree should be cut down at time T star when the increase in the value of the tree over the time interval I can just write T star to T star plus 1, and that is basically P of T star plus 1 minus P of T star, which is approximately equal to P prime T star. This is equal to the interest obtained over this interval by investing amount PT star at little r, at interest rate little r. So at R interest rate. And what is that? That is R P of T star. But we also, it's just a necessary condition. We still don't know if this is sufficient or not. So as in, we have to look at the second order condition, because that way we will be able to, for basically what we have to do here is we have to go for the second derivative test. And if we go for the second derivative test, it will be clear from the second derivative test whether this t star is a strict local maximum, if it's a strict local minimum. What is that? We don't yet know. We know that it is a stationary point. We know that at t star, the present discounted value, the first derivative of that is set equal to 0. It is 0 at t star, but we still don't know whether that t star is maximum, minimum, whatever it is. We still don't know what kind of an extreme point it is, or whether it is an extreme point or not. We just don't know about that. So for that we have to take the second derivative test. So for that we look at the second order condition, and we know f prime t. Let me write that again. F prime t is equal to e raised to the power minus rt p prime t minus r p of t. So now I calculate f double prime t, and for that again I use the product rule, and for that again it's e minus rt, and then it is p double prime t minus r p prime t plus p prime t minus r p of t, this multiplied by e raised to the power minus rt and then a minus r. But what we know from here is that obviously we have to think of what is, if you can just recall the second derivative test, it is this. It is we have to think of f prime c equal to 0, and we have to think of f double prime c. So that means we have to take up now in this case f double prime t star, because that c here in this case it's a stationary point, because we have f prime c equal to 0, and in that question t star is the stationary point. So we have to go for f double prime t star. So that's exactly what we do. And if we go for f double prime t star, that will give us, for that, I mean we put t star everywhere, and then we see that this will be 0, because I know that this is the case. P prime t star is equal to r p of t star. So P prime t star is equal to r p of t star. So that means this expression boils down to 0. So f double prime t star would be this. It is e minus r t star p double prime t star minus r p prime t star. Now we have to look at what this is. If it is greater than 0, less than 0, what is it? Now again in this case we are going to assume some things. We are going to assume that p of t star is greater than 0 and p double prime t star is less than 0. And basically when I assume that p of t star is the current market value. So let's just assume that assume that p of t, now p of t I know is the current market value at time t, at t star, wherein that wherein the present discounted value is going to be maximized, that t star at that time the current market value would surely not be 0 or negative, so it will be positive. So we assume this first. Assume that P of T star is greater than 0, and we also assume that P double prime T star is less than 0. If I assume that P double prime, obviously one more point, if I assume that P of T star is greater than 0, from this, if P of T star is greater than 0, from this expression, if P of T star is greater than 0, R is obviously positive. That means P prime T star is also greater than 0. So that gives us this implies P prime T star is also greater than 0. Now, that just means if you take a look at P prime T star, what that means is that the current market value, it is increasing as we go on in time. But the point to note is, in general, when we talk about the market value, in this case obviously we are concerned about the market value of the tree. So yes, the current market value is positive, and also the current as you go on in time, the current market value increases. But here one assumption we are going to make, and that assumption is that the current market value is increasing at a diminishing rate. That means the rate of increase of the current market value, that rate itself is decreasing, and that just means nothing but the second derivative of P of that just means that the second derivative, that is P prime T star, that is less than 0. So we are going to assume these two things. When we assume P of T star being greater than 0, obviously I have P prime T star greater than 0. But I also assume that as current market value, I know that current market value is increasing as we go on in time, but it is increasing at a decreasing rate. It is increasing at a diminishing rate. So P double prime T star is going to be less than 0. Given all this, if we take up again F prime T star, that is equal to e raised to the power minus RT star, P double prime T star minus R P prime T star. So obviously in this case, this expression is not equal to 0, definitely not the case. P double prime T star we know is less than 0. This expression I am very sure about, it is greater than 0. What does that mean? That just means F double prime T star is less than 0. So what does that mean? That means the T star, which was defined by this expression, this T star is in fact a local maximum point. It's a strict local maximum point. Because here I see that F double prime T star is less than 0, F prime T star, that means that T star characterized by that condition. So I can then write, this implies, or hence T star is a strict local maximum point, and T star is characterized by this condition, that P prime T star is equal to R multiplied by P of T star. That expression, that means again the T should be cut down precisely at time T star when the increase in the value of the tree over that little time interval, t star to t star plus 1, that's exactly equal to the interest rate we are going to obtain over that time interval when you invest the amount p of t star at the interest rate r.